Okay, the question is, a certain mass is driven by excitation through a spring. Figure this. If the its parameter values are m is given. So m is 100 kilograms and c is 400 newton second per meter. K is 10,000. Determine the peak frequency. So you have to find out the peak frequency and the maximum magnitude ratio, or peak at that frequency, what is the magnitude ratio, and upper and lower bandwidth. So I would say upper and lower bandwidth. Okay, usually it looks like this shape, and you know that this is magnitude. So usually we want to see that peak over square root 2. So all this is interest. This is not our interest, because the energy below mp over square root 2 is meaningless. Like, it reduces to quite a lot, like 30 to 40%, because if you are exciting with certain amplitude, like force is 10 newtons and displacement is 4 millimeter, so in the bandwidth you will pick up those frequencies. The magnitude is 4 times point I would say 0.7. That is the amplitude, because the remaining portion is not going to bother our machine. We will keep it simple, like we will consider the bandwidth in that amplitude range. If this is 30, because this is usually mp over square root 2 is about 30% the of the maximum magnitude. So you should, if you go below that 40% decrease, then it is not going to damage our structure, so we will not worry about that. Energy is kind of lost, much of the energy. So in the frequency spectrum, I will show you probably one time. I will show you how to take the Fourier transform of a signal and to find out the bandwidth over there. So let's focus on here. So look at here, this one is the spring. So I would start from, if I have been given this question, so I would start from the modeling of this question. So the modeling, this is this mass. You can either take this approach, or you can just put this degree of freedom on the mass anywhere. It's better to put it in the middle, but this, like this. So when this mass moves to the right, this damper force will push this towards the left, and the spring force will push this towards the left. And you see the spring is connected with both ends here. This end is also moving with displacement phi. This end is moving with displacement. So when you have two displacements, then you subtract the difference, take the difference, because the deflection is the net deflection. So if you write down like this, you will get the wrong answer. So your answer will be correct when you take the difference of the two ends of any element, if it is c or if it is k. Like right over here, if I write it down, minus c x dot minus the difference of this one, but this is grounded. So even if you follow the same approach over here, this end is grounded, so it's 0. So that's why we write down minus cx dot. And usually we write down the first degree of freedom in order to be consistent, that one which is for the mass, which is under consideration. So let's do the Newton second. All the forces, they are equal to mass times acceleration. So I'm going to write down minus cx dot minus k x minus y equals to mx. So if I rearrange it with the order term here, like second order first, comes the next first order, comes the next, and if I split it up over there, it goes to the right hand side. Correct. Now this is our equation of motion, which we derived using the free body diagram and applying the Newton second law. And now we have to just plug in the values. What is mass? 100, c is 400, k is 10,000. So let's plug it in. So mass is 100 kilograms, c is 4 newton second per meter, k is 10 to the 4 x. Now in order to get the, after you do this, you have to find out the transfer function, which is in S domain, which is output over input. Output is this, in S domain this is input. So this is in. So if you do the Laplace transform here and you apply, so you should get 1 over 0.01. I'm sorry, this is S squared. So I wanted to show you the other way, but this is still okay. But let me know if you don't understand this math, then I can further explain. Have you understood this math, or do you want me to explain it one more time? I think in class students they are a little confused, so let me explain this one more time. So suppose over here, if I take the Laplace transform, so 100 s square big X, 4s big X, 10 to the 4 big X, 10 to the 4 big Y. This is Laplace transform. In for the transfer function, we assume all the initial conditions are 0, because you know the forcing function is the transient response is meaningless for the initial part, initial first or 2 seconds motion. So we consider about the when there is a forcing input, and over here this is a force input on the left side of the spring, which is the excitation, correct? So that's why we don't consider the initial conditions for taking the transfer function. So when you do the math here, so this is x over y, this is in y s domain. So what is this? 10 to the 4 over 100 s squared. Agreed? So if you do just divide this again into the denominator, you should get this answer. Have you understood this now? Okay, the students have. Now after you do this, then you find this is our characteristic equation. I will say 0.01 s square plus 0.04 s plus 1. And usually the standard equation is so if you do this, let me show you the standard second order. This is s square plus 2 zeta omega n s plus omega n square. This is the transfer function. Now if you take a look, what is our zeta? C over cc, c over 2 mk. What is our c? It is 400, correct? It is 400. So let's write it down. Zeta, let's find out zeta. 400 is, m is 100 kilograms, k is 10 to the 4. If you do the math, you should get zeta equals to 0.2. You can check it. Now the question is asked, what is a peak frequency? Now if I go to the table, I need to find out the table because I have not memorized those formulas. Look, the peak frequency formula is omega p equals to omega n square, and usually this happens below 1 over square root 2. That is the most important critical point. So omega p equals to This is the required question. And what is omega n? Omega n is square root k over m. And what is square root k over 10 to the 4 over 100? I believe to be 10. And what is this? 10. What is the peak frequency? 9.6, correct? 0.96. Let me check. Square root 2. Is it correct? Why is it not?
Yeah, it's 9.6.
Probably my calculator is not working. So the answer is 9.6 radians per second, correct? Now the next question is asked, determine the peak frequency and the peak magnitude. So let's go back to the table. So the table says the magnitude, um, the peak magnitude is, over here is peak resonance, which is the amplitude is xp over delta t, delta st. So I'm going to write it down here. One minus zeta square. So what is magnitude ratio, which is x over force over here? This is, I can rewrite here this the same thing here. So sorry, this is, what is delta equal to? F equals to k delta, static deflection. So k equals to f over, so I can rewrite here the mp as 1 over k, right? Because you know this, let me take this over here. And the magnitude, the peak magnitude ratio is 1 over k, 1 over 2 zeta 1 minus zeta square. So if you do the math, you should get how much? 2.55 in 10 to the negative 4. That's the maximum, the peak magnitude ratio. Because we have everything. We have k, we have zeta. Now the last thing is asked, find out the upper and lower bandwidth frequencies. So for that I have to show you the formula, this one, which is equation number, I believe, 4.2-9. So let me copy and paste from the book. So if you know zeta, you can find out the upper and lower limit using this formula. So if you solve for this, you should get R equals to 0.727. Another R, I would say R1 and R2 would be, because there are two roots. You will find out when you take the square on both sides, you will get R square, and you have to find out two roots for R. And R1, by using R1 equals to omega 1 over omega n, and R2 equals to omega 2 over omega n, and that will give you the lower bandwidth frequency, which is 0.727 omega n. Omega n is 10, so it is 7.27 radians per second. Similarly, omega 2 would be equal to 11.45